Okay, let us continue. In the last class, we were discussing the phase locked loop, that is the mathematical model of phase locked loop, and we arrived at the non-linear differential equation, which is d psi of t by dt plus k suffix t times sine of psi of t is equal to delta omega for t greater than or equal to 0. Okay, so this is the governing equation for the phase error, where psi of t is the phase error, and we like to understand under what condition will this differential equation imply a movement towards psi of t becomes 0. So that is our point, and we said that this non-linear differential equation can be represented its behavior in terms of a diagram called phase plane plot. So that's what we are going to discuss in this lecture. So we like to just see how that happens. Okay, we like to study this through a device called a phase plane plot. So the phase plane plot essentially is a plot of these quantities, the derivative of psi of t versus psi of t, right? So that is at any time instant, how is the derivative of the psi of t related to the quantity itself. Okay, so that is at any time instant we plot psi of t on the x-axis and d psi by dt on the y-axis. Okay, so x-axis is the instantaneous phase error psi of t. We can remove the time dependency. In fact, if you want, let us simply put psi, and in the y-axis also we can remove the time dependence d psi by dt. Okay, therefore x-axis is the phase error. Phase error, so that it does not okay, let us remove the time parameter so that it does not confuse us. Okay, just plot d psi by dt versus psi. So now what is the nature of this non-linear equation? D psi by dt plus kt times sine psi is equal to del omega. Okay, now you can think of this is like y versus x. Okay, therefore you can write that equation as y plus kt times sine x is equal to delta omega. Now let me call this as equation number 2 and this one is equation number 1. Now what kind of equation is this? Equation 2. See, we have a sinusoidal function. Okay, what is the value of this function? Let's say psi equals 0. When psi equals 0, then y is equal to delta omega. So you may have a function like that. This point corresponds to, when psi equal to 0 corresponds to omega, delta omega. So now how can you find out the peak value? First let me plot this point. When psi equals to 0, it reaches the peak point. Okay, now let us try to find out what is the peak value, I mean maximum value. Now you substitute x equal to minus pi by 2. X equal to minus pi by 2, then you will get y plus k suffix t minus 1 is equal to delta omega. Therefore y is equal to delta omega plus k suffix t. So probably this point is minus pi by 2, so it has the maximum value. So therefore your function goes like this, So this is my d psi by dt along the y-axis and psi along the x-axis. Okay, when you substitute x is equal to plus pi by 2, then y is equal to delta omega minus k suffix t. So this is a minimum value and this one is maximum value. So maximum value, and then like this, let's say this is minus pi by 2. Please bear with me, like this figure is not in the scale. Okay, so this point is delta omega minus k suffix t, and this point is delta omega plus k suffix t. Okay, let me call this as point A, and the minimum point let me call point B. At these points A and B, d psi by dt becomes 0, right? That is the way to look at, we need to look at this. So at one point it will be kt plus delta omega, and at other point it will be delta omega minus k suffix t. So this is the phase plane plot. So the study of this phase plane plot is very interesting and gives us all the insight that we need to understand. Okay, now how a phase locked loop locks itself, that is a question that one should ask. So let me draw the plot again, this phase plane plot. Like this. Okay, this point is minus pi by 2, it reaches the maximum value, and this point is plus pi by 2, so delta omega minus kt, and this is delta omega plus kt, and this is d psi by dt, and this one is psi. Okay, the phase plane plot is very interesting. Okay, and this phase plane plot gives us all the insight that we need to understand. Now we should ask ourselves like how a phase locked loop locks itself by itself. So what we are saying is the following: the dynamics of the phase error will be such that d psi by dt and psi at any time instant must be consistent with respect to each other through this diagram. Okay, let me put this one somewhere else, like this. Okay, now if d psi by dt is let's say this value. Okay, let me call this point is y1, and this point is x1. Okay, so the corresponding phase error must be this point, and this is the derivative of that. Finally, it is a solution of an equation depicted diagrammatically in some sense. Okay, when psi is equal to x1, then the solution will be y1. So the value of d psi by dt and psi must satisfy this relationship. Okay, which is shown in the graphical format at any point in time. So let us assume to start with when the input signal was at the constant frequency. Okay, that's what we have done. So we are assuming that the input signal was at the constant frequency, and suddenly there is a step change in the input frequency. So in that case, when the input signal was at a constant frequency for a long time, okay, so let's assume that the loop was in the locked condition earlier. Now when the loop was in a locked condition, where was it? Where will it be? Locked condition means what? Your phi of t, is approximately equal to theta of t, right, locked condition theta of t. That means what, your psi of t is approximately equal to 0. So this point is psi of t is equal to 0, therefore it was here. This point indicates locked condition, because at this point your psi becomes 0, the phase error will be 0. Therefore you were at this point. Now in our discussion, assume that PLL was initially locked. Let us assume that the phase locked loop is initially locked. Therefore you were at this point. Let me draw the same figure again, like this. So this is a point, let me call this point is B. At this point your psi equals 0. Okay, at point B your psi equals 0. Okay, because at point B your psi was 0. Now what will happen? Let us also understand another significance in the phase plane plot before you take the argument further. Let us consider at a certain point in the phase plane plot where d psi by dt is positive. What does it mean? That means what I am saying, d psi by dt is positive, means greater than 0. So if this is so, if this condition is true, then what will be the nature of psi of t as a function of time? Okay, psi of t as a function of time. If this condition is true, then what will be the nature of psi of t as a function of time? What can you say about that? Okay, remember d psi by dt is a derivative, and this dt is small time interval, right? So if you recall from your derivative definition, you take x of t minus x of t minus tau and divided by tau, right? So that is your derivative. You take very small interval. Let us keep aside this definition. So this dt is very small amount of time, okay, infinitesimally small time, and this time interval must be positive. Okay, so dt is increment in time, so therefore this dt will be always positive, always positive. So time only progresses forward, right? It never goes backward. Therefore d psi will always imply positive increment. So d psi by dt greater than 0 implies d psi is what? Will be greater than 0. Okay, so increment in time, dt indicates increment in time, so dt is always positive. That means d psi is must be greater than 0. Okay, therefore d psi will always imply the positive increment. Therefore if you are at a particular point in this phase plane plot, let's say in this point, if you are there, let's say this point is y1, then in this point where your d psi by dt is greater than 0 with the derivative is positive, it implies that from this point y1 onwards the phase error will increase as a function of time. Okay, from this point, the corresponding point here, this will be x1. So this is my phase error. As I said, in this point your d psi by dt is greater than 0. That means what? This is greater than 0, it is implied. Therefore, this d psi also greater than 0. That means what? Your phase error is increasing. It is not coming down because it is non-negative quantity, positive quantity. Therefore, it is increasing. So, the phase error will be increasing from that point onwards, from x1 onwards. Therefore, the phase error will increase as a function of time. At point y1, the phase error psi will increase as a function of time, because the derivative is positive. So, psi of t must increase as a function of time. So, slope is positive. Okay, so this will imply an increasing value of psi of t. So, d psi by dt is greater than 0, which implies an increasing value of psi of t. Increasing value of psi of t means what? This is my x axis. So, it is moving towards the right hand side. With respect to time. Okay. So, this is very important point we need to understand. So, I am talking about temporal behavior, time behavior of the signal. Okay. So, but in this plot we are not showing time behavior. So, this is psi and this derivative of psi. Of course, psi is a function of time. So, we are talking about temporal behavior, I mean time behavior of the signal, time behavior of the phase error. Because d psi by dt is positive at a certain point, what we are saying is that that will imply that the dynamics will such that the phase error will increase as a function of time. Similarly, on the other hand, when d psi by dt is negative, let us say d psi by dt is negative. What does it mean? It takes negative value. But as I said, dt will be always positive because it is increment in time. That will never be negative. That means the denominator is greater than 0, then obviously this implies your d psi is less than 0. That means what? Your psi will decrease as a function of time. Psi will decrease as a function of time. So, this is a subtle concept, so let me go a little slowly. So, what does it mean? If you are on the positive side of the phase plane plot, what is the positive side? Upper half plane above the x axis. This is my positive phase plane plot. And this one is negative phase plane plot, where the value will be negative. Okay. So, if you are on the positive side of this phase plane plot anywhere, we will move along the trajectory. Let me like this. So, we will move along this trajectory like this, because in the positive direction psi will increase. That is what we said in this condition. Where is it? Yeah, when d psi by dt is greater than 0, then this is greater than 0, that implies d psi also greater than 0. If d psi is greater than 0, that means your psi is greater than 0, it is increasing, your phase error is increasing. That means here in this point your psi equals to 0, so the psi is increasing, that means what? You are moving towards the right side. Okay, so the d psi by dt and psi of t always have to be related by this trajectory. Okay, you can move along this like this, like that it moves. Okay, therefore when d psi by dt is positive, that is you are in the positive side of the phase plane plot, then positive half of this plane, then phase error will try to move to the right. Okay, you will move along the trajectory to the right. Okay, because the phase error has to increase as a function of time. No matter where you are in the positive side, you will keep on moving to the right. In case if you are in the negative side, we will keep moving to the left along the trajectory. I think I wrongly told you, 1 second. Let me say this is my positive side of the phase plane plot, then this is negative side of my phase plane plot towards the left of my y axis. Okay, so right side of your y axis is positive phase plane plot, positive half of the phase plane plot, and left side of your y axis is negative half of the phase plane plot. So if you are in the negative side, then we will keep moving to the left along the trajectory. But in this phase plane plot, the time dependence is not obvious. But the fact that this d psi by dt is positive, it will imply that psi of t has to increase as the function of time, right? If d psi by dt is greater than 0, then it has to increase towards the right. In case if d psi by dt is negative, then your psi will move towards the left hand side. But we are not showing exactly what is the rate at which it moves, at what rate it is moving. But it has to move in the negative direction if d psi by dt is less than 0, and it has to move in the right hand side direction if d psi by dt is greater than 0. Okay, that's all we are saying now. So we are not able to say at what rate it will move, but we don't know. Okay, sorry, but we do know that that is actually moving in the right hand side, to the right side like this, or it moves in the left hand side. It may move in the left hand side. Okay, so in this case I move to the left hand side because my d psi by dt is less than 0. Therefore psi of t has to increase in this direction towards the left hand side direction. Sorry, decrease towards the left hand side direction. If d psi by dt is greater than 0, you have to move towards the right hand side. Okay, so that's all we are saying. Okay, so we don't know, of course, at what rate it increases and at what rate it decreases, but the fact that it increases means that it will move along this direction, right to left to right. Okay, so this is the way we understand the dynamics of nonlinear system, something called a phase plane plot. So what I am really telling you is how a phase plane plot should be interpreted to understand the dynamics. Now suppose initially your phase plane let's say you are at this point, let me say this point is B, then loop is initially locked because at this point psi equals 0. So where will you start moving now? Will start going towards the right till you reach this point C. Okay, therefore you move towards the right hand side. Okay, initially you are at point B. Okay, now you will start move towards the point C, and you will stop at this point. Beyond that you will not move. Why? Because at that point your derivative is 0. Okay, if you move slightly, if you slightly move on either side of point B, you will move away from this point B. I think again I made a mistake. Let me correct this. Oh my god. I confused with the left half plane and right half plane. Okay, so this is upper half plane. Okay, so above the x axis is called upper half plane, and below the x axis is called lower half plane. Let us be very clear, right? So now let us consider this point. Maybe let me draw the figure one more time, like this. Suppose you are in this point, let's say this point is D. Okay, now what will happen? You are in the lower half of the phase plane plot. Okay, so you will move away from this point D, and so if you are in the lower half of the phase plane plot, you will move towards the left hand side, and finally you reach this point C and you settle there. Okay, because in this point your d psi by dt is what? Less than 0. If d psi by dt is less than 0, that means what? Your dt is always 0, greater than 0. So this implies that your d psi is less than 0. That means if d psi is less than 0, this implies that psi should be less than 0. Therefore it has to decrease. Decrease means it should move from right to left. Once you reach this point, C point, you will settle down there. So that is a stable operating point of the phase locked loop. So in summary, in the upper half plane, we will move along the trajectory to the right hand side like this. Suppose you are at this point B in the upper half plane, then you will move towards the right hand side. Even if you are stay here, then you will move towards the right this. Therefore, whenever your point is in the upper half plane, it goes like this and it settles down there. If you are in the lower half plane, you are coming back to this like this. Okay, in the lower half plane, it will move along the trajectory to the left side, and that leads us to the conclusion that point C is a stable operating point of the phase locked loop. Phase locked loop. Okay, so at point C, let's say at point B, when there is an attempt to move away from this let's say at point C, okay, at point C, when there is an attempt to move away from this point C, then it will try to return to this point C condition again. By chance somehow if you are moving away from this point and reaching here, then again there is a more chance to come back to this point C also. In case if you move this direction again, then you are forced to come to this point C. So point C is a stable operating point, as I just mentioned earlier. Okay, and the implication of that is when it attempts to move away from point C, that is the operation attempts to move away from point C even by a small amount, then it is forced back to point C again. Therefore, we can also call it the steady state operating point. Point C is called a steady state operating point. So, what we are basically trying to say is that in this condition, the loop will try to arrive to this point C. So, when you start with the psi equals 0, so that means point B, psi equals 0, it will not stay at psi equals 0 because of the step change in del omega, right? Even in your carrier frequency, if you recall, I said in the last lecture, x of t is equal to a times of cos omega ct for t less than 0, right? Then your modulated signal x of t is equal to a cos omega ct plus delta omega for t greater than 0. Therefore, a step change in the carrier frequency. Carrier frequency when t greater than 0. So, therefore, because of the step change in the input frequency, it will try to reach a point where there is a steady state error or phase error. Because of this introduction of the step change, what happens? You try to move from this point to this point. So, there is a steady state operating point. But at that point, at point C, there is no frequency error because d psi by dt is equal to 0. Okay, recall that d psi by dt is equal to 0. What does it mean? If d psi by dt is equal to 0 means the instantaneous frequency error will be 0, because psi is the instantaneous phase error. Psi is phi of t minus theta of t, instantaneous phase error. If you differentiate d psi by dt, what does it mean? Instantaneous frequency. This is psi is instantaneous phase and this is instantaneous frequency. If d psi by dt is equal to 0, that means the instantaneous frequency error will be 0. So, there is no error in the frequency. If psi of t is the instantaneous phase error, then d psi by dt is the instantaneous frequency error. So, the loop would have locked itself, that is VCO would have locked itself to the new frequency. Okay. Initially it was FC, now it is locked to FC plus del omega, no problem. So, locking in the frequency is not at all a problem. Okay. So, therefore, the voltage controlled oscillator would have locked itself to the new frequency. Therefore, there is no frequency error at this stage. But that reduction of frequency error to 0 is associated with the finite phase error in the process. So, that means the phase error does not remain 0. So, let us call this steady state phase error. Phase error psi suffix ss, and this one is some value, and this value is governed by the point C, this point. Okay. So, let us say, and this distance is called psi ss, steady state error. Okay, and this is the steady state error, that distance, this one, steady state error. So, we will write down the expression for psi ss a little later, but we can also see that the steady state frequency error, how much is this? Equal to 0, because it is in its locked condition. Okay. Therefore, the final point is steady state phase error is equal to psi SS steady state frequency error, how much? 0. Okay, so that's it about the first part about our phase plane plot. The second part was we will try to figure out how the locking actually occurs. Okay, so till now we discussed the loop is in the locked condition. If it is locked condition, then we said psi equal to 0. So this is my point. By any chance it moves towards the right side, or okay, and it reaches a stable point. So this is the quasi steady state. Now what we are saying is like how we can achieve this steady state. That is the second part. Okay. First phase is over now. The second part was we tried to figure out how the locking actually occurs, how the locking will occur. Now in this case we have to go through a non-linear model of the loop. See here we said the loop was locked. Locked means phi of t is approximately equal to theta of t. In that case what did we say? Sine of phi of t minus theta of t is equal to approximately equal to phi of t minus theta of t. Therefore this non-linear function sine becomes a linear function. Now we are saying how this how locking actually occurs. That's what we are going to discuss now. In this case the loop is not locked, okay, it is in the process. So in that case we cannot use the linear model, we have to use the non-linear model. Okay, so we have to go through the non-linear model of the loop, because we found that the phase locked loop actually is a non-linear system, right? In fact we obtained a differential equation description for the operation of the phase locked loop. In particular we arrived at this non-linear equation d psi by dt plus k suffix t sin psi is equal to del omega. This is the equation which we obtained by using non-linear differential equation, and which specifies the instantaneous phase error between incoming phase and the VCO output phase. Incoming phase is phi of t and VCO output phase is theta of t. So we found this equation for phase error, and this is the non-linear differential equation. And you try to look at the equation of try to look at the operation of the PLL by considering what does this differential equation imply in terms of its operation. So to analyze this non-linear differential equation, we took the phase plane plot, a graphical approach, a graphical picture of the differential equation, and that graphical approach we called a phase plane plot. In the phase plane plot, basically we plot d psi versus psi. So that phase plane plot obviously becomes the sinusoidal function with a peak occurring at when sin c is either +1 or -1, right? So this guy occurs maximum when sin c equal to -1. So when sin psi is -1, then d psi by dt maximum is delta omega plus kt, that we already discussed, and minimum occurs when sin psi is equal to +1. Therefore d psi by dt minimum is equal to delta omega minus k suffix t. Okay, if it is -1, that gives you the peak value as kt plus delta omega, which is the positive value. At psi equals 0, at this point the intersects the d omega by dt axis at delta omega. like this. When psi equals 0, then it intersects the y-axis. Let's say this point is A. When psi equals 0, then this point intersects the d psi by dt axis at the point is delta omega. I'm sorry, the plot is not as we like this. I'm sorry, this also again wrong. Oh my god. Like this. Let's say this point is delta omega and the peak value is delta omega plus kt. That's what I want to say now. Okay, so in this point d psi by dt is equal to delta omega. Okay, and then we said if your modulating signal was a unit step function, then of course we cannot plot the phase plane plot for the general signal. So that is why we assumed the input modulating signal is a step function with the magnitude of delta omega times u of t. Okay, so you have to do it for a specific signal, and the specific signal that we considered was your step function. So for this case, assuming that initially the loop was locked at the carrier frequency, we found that eventually the operating point will move on the trajectory and finally it reached this point. Okay, and the second important point is the motion on this trajectory. How does it move? Okay, whether will it move to the right or it will move to the left. So it moves to the right if you are in the upper half plane of the trajectory. The motion will be to the left if you are in the lower half plane of the trajectory. So, and based on these arguments, we concluded that this point A, okay, is a stable operating point. Sorry, point C. Let me call this point C. Maybe one more time. Yeah, this point C is called a stable operating point. Okay, stable operating point of the loop, which means that after the frequency step has been applied, the loop will eventually try to come to this point C, because at this point your d psi by dt is equal to 0. This is my y axis, d psi by dt. Okay, why is it d psi by dt equals 0? Because y axis is 0 at in this axis, x axis. So if d psi dt becomes 0, that means there is no further movement in the operating point, no derivative. Okay, d psi by dt equals 0 means what? There is no derivative. That means there is no slope. So psi as a function of time becomes constant value. Okay, we said psi is a function of time, but now your psi of t becomes psi at a point C. Therefore it becomes a constant. At the constant value, and the constant value is this much. What is that constant value? Like this, and this is a constant value when psi is equal to psi SS, steady state error, or you can write this one, psi of t is equal to psi SS. So whatever is the value of psi at this point C, at this point, is the steady state value of the phase error. Okay, in fact there will be many such points, but they are all periodically placed. Even you can say this point also, but again these points all are periodically placed. So the next such a point will be at this point will be like a psi ss plus 2 pi. Okay, it keep on goes like this, not this one, this one. So this is next psi ss. Let's say this is psi ss1 and this is psi ss2. So because it is periodic function, right, therefore the steady state value also periodic. So in as much as phase is anyway specified modular 2 pi, right, it doesn't matter which point you lock on to. Okay, it hardly matters. So somebody says phase error is 1 degree, then this is the same as 361 degree. Okay, you cannot distinguish between the phase error which is of 1 degree or 361 degree. It is really the same thing, so that doesn't really matter. Okay, either you take this point as a psi ss or this point as psi ss, because it is a periodic function. Okay, now let us proceed further and just do further little bit of discussion on what we get from the phase plane plot. We said this psi ss is the steady state error, and we also said that steady state frequency error would be 0. Okay, so what is a non-linear equation? D psi by dt plus k suffix t sin psi is equal to delta omega. Now look at this equation. Let me call this is equation number 3. I guess first two equations I wrote. Now at the stable point, what is the value of d psi by dt? Your d psi by dt becomes 0 at the stable point. So in this point, now we are asking what is d psi by dt, which is 0. So substitute d psi by dt equal to 0 in this equation, then 0 plus k suffix t sin psi is equal to delta omega. So this sin psi becomes sin psi ss. So psi ss is equal to sin inverse of delta omega by k suffix t. Okay, so let's say this is equation number 4. It shows some very important fact, that is, if you want the steady state phase error to be small, generally we would like to have a small steady state error. What should happen to KT? KT should be large, because it is inversely proportional. So KT will be large for a given frequency step at that input. So if you want a steady state phase error, this is phase, steady state phase error to be small, the argument should be small, because if we know this sine inverse, right? Okay, so argument should be very small. Therefore the conclusion is, for a small value of steady state phase error, k suffix t should be large. Now what is k suffix t? It is the loop gain, right? Therefore this whole point implies large loop gain. So if the loop gain is large, then the steady state phase error will be small. So basically we are saying that we require a large value for the loop gain, and now we require a large loop gain not only for small steady state phase error, but also for another very important reason. Okay, let's see what that reason is. So all this discussion was nicely concluded, and we could demonstrate through the phase plane plot that indeed the loop will lock in as much as the phase error thus come to a small value, but it doesn't become 0, of course. Okay, so if you want to make it 0, if you want to make this steady state error equal to 0, so ISS equals 0, you must have a very large value of loop gain, because look at this equation. Your psi SS is equal to sine inverse of delta omega divided by k suffix t. If I want to make this steady state error to 0, then this kt should be infinity. So sine inverse of delta omega by 0, this is equal to 0. Therefore your sine steady state phase error becomes 0. Therefore larger the value of the loop gain, smaller the steady state phase error. But nevertheless, whether large or small loop gain, the important point was that it has come to the stable point. Okay, so it should have a stable point. Okay, now the second important thing to note is that for lock to occur, the phase plane trajectory or phase plane curve should intersect the x axis. So this is second point. For the lock to occur, the phase plane curve should intersect the x axis. What is the x axis here? Psi. So that is the important point that we will discuss now. And in order for that to happen, what do you need? You need to make sure that delta omega minus k suffix t is less than 0. Okay, that means what? Your delta omega is less than k suffix t. So the lower peak of this curve should be negative. I mean the lower peak of this curve should be negative, so which implies that delta omega should be less than the loop gain. So the loop gain plays a very important role in the operation of the system. So you have a plot like this, and what is this point? This point is delta omega minus kt. And this point is delta omega k suffix t. Okay, the phase plane plot intersects. At what condition it will intersect? When delta omega minus kt will be less than 0, otherwise it will not intersect. Okay, so it should be negative value. Okay, in the lower half plane, this delta omega, because your d psi by dt is minimum value. Minimum value is delta omega minus kt, and this will be less than 0. Less than 0 means it falls on the negative side. If this condition is not satisfied, then what will happen? Your phase plane plot will be like this. So in this case, your delta omega minus k suffix t is greater than 0, because this is a positive value, right? And this point is delta omega minus k suffix t, and of course this is greater than 0. If greater than 0, then you never intersect the psi axis. So the loop gain plays a very important role in the operation of the system. So when delta omega minus kt is less than 0, implies delta omega is less than kt. That means what? The lower peak of this curve should be negative. I mean the lower peaks of this curve should be negative, which implies that this curve intersects the x axis. So delta omega should be less than k suffix t. So a few points to be noted in this. So large value of the loop gain will imply small value of the steady state phase error. Large value of the loop gain implies small value of the steady state phase error. And the second point is the large value of the loop gain will also imply a large value of what is called a lock range. Lock range of the loop. So loop gain is a way besides what is called the lock range or locking range of the PLL. Therefore, if you maintain the large gain, then the loop will lock. So locking range of the PLL phase locked loop is equal to k suffix t. Large lock range implies large value of k suffix t, because locking range of the PLL is the maximum frequency step that you can employ, that you can have at the input, but still the loop is able to produce a steady state situation. That if frequency error is 0, that is the VCO exactly locks to the input signal frequency, but there will be a phase error. Large lock range requires that we choose a large value of kt. Okay. So for example, let us assume that your loop gain has some fixed value. So let me say I have chosen the fixed value to be, let's say, 2 pi times 50. Okay. Now let us consider my k suffix t is equal to this pi, 2 pi times 50, so 100 pi. Okay, so let me now plot the phase plane plots for different sets of delta omega. Let's say your my delta f is equal to where is this? Okay, it is here. Delta omega minus kt is less than 0 to cross the x axis, I mean psi axis. Now let us take my kt is equal to 2 pi times, actually my kt is delta omega, so that I can write as 2 pi times delta f, right? So let's say delta f is equal to 55 hertz. Let me start with 55 hertz. Then let us see what will happen. So your k suffix t is equal to 2 pi times 55. That means what? You are applying the frequency step of 55 hertz at the input of your modulator. You have FM modulator. So the input is m of t is equal to 55 hertz of u of t. Okay, and here you are applying the carrier frequency cos omega ct, a times cos omega ct. This is your modulated signal. So there is a jump of 55 hertz. And let us, sorry, this is we are assuming this kt is equal to wait a minute, I am confusing you. Okay, let's say assume kt is equal to 50, therefore this is 100 pi. Let us assume like this. Let's say delta f is equal to 55, then what is my delta omega? Delta omega is equal to 110 pi, right? So therefore my assumption is kt is equal to 100 pi. Now if delta omega is equal to 110 pi, then this delta omega is greater than kt. In this case, what will happen? Your phase plane plate will be like the phase plane plot will be like this. It will not touch the psi axis. So this corresponds to delta omega is equal to 55. Why? To cross the x axis, your kt minus delta omega should be less than 0. That means kt is less than delta omega. I'm sorry, where is it? Sorry, delta omega minus kt. I'm sorry. That's what I'm thinking. Why is it coming in the wrong way? Delta omega minus kt must be less than 0 to cross psi axis. That means what? Delta omega must be less than kt. But here, what is the situation? Delta omega is greater than kt because 110 pi is greater than 100 pi. That's why. Now let us take delta omega is equal to let's say 48 hertz. So in this case, what happens? It is 48 pi. Let us, I'm sorry. Delta f is equal to 48, then delta omega is equal to 2 pi times 98. So this is how much? So 96 pi, and again this 96 pi is what is this 96 pi? To cross the x axis, what is the condition? The condition is delta omega should be less than kt. So 96 pi is less than your what is your kt? Kt is 100 pi. So the condition is satisfied now. Therefore your plot will looks like this. It crosses. So this is delta f is equal to 48 hertz. So it crosses the x axis. Right. Now let me take delta f is equal to 24 hertz. So in this case, delta omega is equal to 48 pi. Again this 48 pi is less than your kt. So again my plot crosses like this. So this will be delta f is equal to 24. Then you can put one more plot also like this. Maybe this is delta f is equal to 12. Okay, when you take a 48 hertz delta f, then it will almost just intersect now. So now we will be in the situation like that. So a stable operating point will exist. So for delta f is equal to 48 hertz, 24 hertz and 12 hertz, we have the stable operating point. What is that stable operating point? This one, then this one. Maybe I can change the line, and then this one. These are the stable operating points. Okay, so a stable operating point will exist for 48 hertz, then 24 hertz and 12 hertz. But the corresponding steady state error would be quite large. So your steady state error del psi is equal to sine inverse of delta omega divided by k suffix t. So if we make half of this, okay, 48 to 24, as you can see, the steady state phase error will come down accordingly. For 48 hertz, what is your steady state error? This guy, right? So this pink color point, this point is 48, and this one is for 12 hertz. Therefore, this is my steady state error psi SS2, and this one is psi SS1. So when the frequency is decreased by double, my steady state error also will come down accordingly. Again, if I make half of it, then 24 becomes 12, then this is my new steady state error, this one, psi SS1. Okay, so I have a sequence of curves for 55 hertz. This is delta f equal to 55 hertz. So I have a sequence of curves, okay, which I have plotted for delta f equal to 55 hertz, 48 hertz, 12 hertz and 24 hertz and 12 hertz. So this picture says it all. It demonstrates very clearly that as you increase the loop gain, you get better and better performance from the phase locked loop. But even in the steady state, I cannot always use the linear approximation, okay, that I have discussed earlier. Because for a linear approximation to be valid, what is the assumption that you made? Psi of t is very small. Suppose your loop gain is not very large and the delta omega is quite large. You could have the large value of the steady state phase error. Therefore, you cannot use the linear model. And for that value of the steady state phase error, I cannot assume sin psi t is equal to psi t for large psi of t. Therefore, I cannot use a linear approximation. So the linear approximation that we considered would not be available for us to use even in the steady state, if your steady state phase error is not very small. So it is imperative that if you want to use a linear approximation in the steady state at this stage, and it is useful to look at the small phase error approximation or linear approximation to study the steady state behavior of the loop. At least approximate behavior if not exist. So whenever you want to use a linear approximation, then you have to use steady state, low value of the steady state error. Therefore, when psi SS of t, this is a constant, right? Psi SS is a constant, is small, we can use the linear approximation. Linear linear approximation of the phase locked loop can be analysis. What does it mean? Please remember that your final equation from which we derived this differential equation first, that your theta of t was equal to k suffix t times integral of sine of phi of alpha minus theta of alpha times d alpha. Okay, what is theta of t? Theta of t is the instantaneous phase of the VCO output. VCO output. So if you are going to use a linear approximation, that sine function can be removed, and we can simply write it as theta of t is equal to k suffix t integral of phi of alpha minus theta of alpha times d alpha, if you want to use linear approximation. Okay, now let's say this is equation A and this is equation B. So if you want to convert this equation B into the corresponding differential equation, then what will you do? You differentiate both sides with respect to t. Therefore d theta of t by dt is equal to k suffix t times phi of t minus theta of t. So this is equal to k suffix t times phi of t minus k times theta of t. So rearrange this, then it becomes d theta of t by dt plus k suffix t times theta of t is equal to k suffix t times phi of t. Right? So let's say this is equation C. So this is my linear differential equation. So when the linear approximation is valid, the loop is now described at or near the steady state by a linear differential equation. And when that is so, it is possible to study it much more conveniently, because we know how to study this linear differential equation. Let's say by using Laplace transforms. In fact, we can obtain the transfer function model of the loop. For example, I could define a loop transfer function. Loop transfer function. Okay, sometimes called closed loop transfer function. So this closed loop transfer function is defined as the ratio of the Laplace transform of the output and the input. So what is the output here? Output is your VCO output, right? That is your theta of t, the final phase of the VCO. Now what is your input? Input is your psi of t from your FM signal, the incoming phase function. So I define the loop transfer function, which is denoted by h of s is equal to Laplace transform of the output. Let me put by theta of s. This is capital theta, big theta, divided by capital phi of s. So this is my loop transfer function, closed loop transfer function. So definition of any transfer function is Laplace transform of the output variable to the Laplace transform of the input variable. That's what we are doing here. So what will be the value of the transfer function here? You take the equation, okay, this differential equation C, d theta of t by dt becomes s times theta of s, and then so on and so forth. You can easily write down the equation. Okay, so therefore this equation becomes s times theta of s plus k suffix t times theta of s is equal to k suffix times phi of s. Now in this, theta of s is common, you can take out s plus k suffix t is equal to k suffix t times phi of s. Okay, now the transfer function is output by input. What is output? Theta of s divided by phi of s, which is k suffix t divided by s plus k suffix t. So therefore your transfer function is k suffix t divided by s plus k suffix t. This is my h of s. You take the inverse Laplace transform. So this is my h of t is equal to k suffix t times e to the minus k suffix t, and you multiply u of t because you are applying the unit step function. So this is the impulse response function at the output, and the impulse response at the output of your system. Now this equation shows that an impulse function, this is my del of t and this is my h of t. So how does the del of t looks like this? A pulse at t equals 0. But my system in the output is does not produce an impulse function at the output immediately. It goes through an exponential function. It goes through like this. Okay, so this equation, this impulse response shows that an impulse function at the input does not produce an impulse function at the output immediately. On contrast to this, what does it produce? It produces a decaying exponential function k suffix t times e to the minus st. So an impulse function at the input does not produce an impulse function at the output, but some other impulse response, okay, which is exponentially decaying response. Ideally, if you don't want the system to do any distortion of any kind, then this h of t should be equal to del of t itself. Okay, if you don't want any distortion or anything else, whatever you are giving the same thing you wanted in the output. Now the question is obviously, how can I make this to del of t? How can I make this k of t times e to the minus st to del of t? You make kt times t. I'm sorry, this equation I wrote wrongly. This is kt times t. Kt times t. Now somehow I would like to make this exponentially decaying function in terms of del of t. What can I do? You increase k suffix t, keep on you increase. If you keep on increase, then what happens? Kt increases multiplied by e to the minus k suffix t, and t increases. If k suffix t increases, e to the minus large value. So this will be equal to what? E power minus infinity. Okay, it will be very less value. Therefore, your signal will be concentrated at kt only. Therefore, your h of t becomes del of t as k suffix t tends to infinity. In that case, your theta of t becomes your phi of t. That's it for large loop gain. So no matter how you looked at it, okay, we reached the same result. Now let us talk about demodulation of phase modulated signals. Okay, so before we proceed further, suppose we want to demodulate the phase modulated signal. So in that case, how can I use the PLL for this purpose? Right, I want to use the PLL for demodulating the phase modulated signals. So what will I do, or how should I do that? You just integrate the output of the FM demodulator. Okay, so you just integrate EV of t, the output of your output, you just integrate it. Okay, that will produce the required demodulator output. So you have the FM demodulator. Either you use it phase locked loop or whatever it is, you give it to the integrator, then that will be your M of t. So this is my received signal X or of t. So it's a standard result. So the same circuit, same setup, same argument, we can use it for demodulating the phase modulated signal. Okay, so let me summarize some points about your phase plane plot, whatever we discussed till now. So we derived this H of S is equal to K suffix t divided by K suffix t plus S. Now what is the bandwidth of this filter? Actually this is a filter, right? Filter transfer function. Let's say 3 dB bandwidth. Okay, so it is a low pass filter. If we plot this, then it looks like a low pass filter. As omega increases, the value will come down. So it will attenuate the signal more and more. So what is a 3 dB bandwidth? When S becomes KT, then the bandwidth will be a 3 dB point. Therefore, you can think of this KT as the 3 dB bandwidth of the loop, right? And you can think of KT as a lock range. The KT has a lot of significance, and also this KT decides the steady state. Decides the steady state of the phase error. Steady state value of the phase error. Okay, KT can also be considered to be what is called a loop bandwidth. That's what I wrote here, loop bandwidth. Okay, so KT can also be constructed with in this particular case, so the loop bandwidth. So what we are saying is that if you want a good performance from the phase locked loop in terms of steady state phase error, in terms of lock range, and consequently in terms of demodulation of FM signal, you would require either a large loop gain or equivalently a large loop bandwidth. Okay, so if you want the PLL works well as an FM demodulator, against you want the large value of, again you want a large value of KT. Okay, so the PLL, your phase locked loop, works very well as an FM demodulator, then you need a large value of K suffix t. So that's it. So these are the conclusions of our phase plane plot. Now let me list out some few remarks. Remark 1. Now large loop gain is not always possible, right? It is very difficult, at least in your receiver circuit. Okay, it also has some problems associated with it, okay, which will be go into right now. But it is usually not easy to realize a very large loop gain. So you need to think of improving the performance. Okay, so let us try to think of how to improve the performance when we do not have sufficiently large loop gain. If you don't have large loop gain, then how can you improve the performance? And one way of improving the performance is, remember the loop filter. Okay, so the analysis that we have done is for a very specific situation. Okay, please remember that we have removed the loop filter to make the analysis very simple. So one of the advantages of including the loop filter is that we can relax on this condition that we have a loop gain. So therefore the loop gain Kt is increased by employing the loop filter. If you put a loop filter, then the gain will be improved. So only thing is, the moment we have the loop filter, our analysis becomes much more complex. So till now whatever we discussed, that that analysis was based on the condition that there was no loop filter. Now what I am saying is, I need Kt should be larger. To achieve large value of Kt, I am including the loop filter. But if you insert the loop filter, then whatever the equation, whatever the analysis we have done, that completely changes. Isn't it? So because I can no longer write that differential equation so easily. So I have to also consider how the filter affects the differential equation. So far the phase detector output, except for the multiplication by the loop gain, was directly going into the voltage controlled oscillator input. So it is very easy to relate through the integral or through the differential equation. The moment you add the additional loop gain, that is the loop gain is coming in between your voltage controlled oscillator and your phase detector, then there will be a problem. Okay, and that affects the entire description in terms of either differential equation or integral equation. Okay, so it cannot be done, so just becomes a little more complicated. Now the second remark is look at the value of Kt. It is, this Kt is given by 1/2 times AC, AV, Kd and mu, right? So there are so many factors which determine the value of the loop gain. First of all, input signal amplitude. This AC is input signal amplitude, and this input signal amplitude is not the same for every time. Okay, and this input signal amplitude itself has an effect on the loop gain. Sometimes your signal will be strong and sometimes your signal will be weak. Now another thing, of course, more or less constant of the phase locked loop itself, right? This AV is associated with the phase detector. So what is mu? Mu is the gain that you have incorporated in the phase locked loop. Okay, so these three constants AV, Kd and mu are associated with the loop. But what about AC? This AC is the input signal amplitude, and this input amplitude is associated with the input signal. But that is not a very nice thing to have, because you don't want a loop design to be dependent on the amplitude of the input signal. Because if that is so, the input signal has the weak amplitude, the loop gain goes down. Suppose you have transmitting antenna, and this is my receiving antenna. Let's say the distance is 10 kilometers. That time your AC value will be some value. If you come very closer, then it has some receiving antenna. If it is far away, then it has some other value. Therefore, depending on the location of your receiver antenna, your input signal amplitude AC will change. Okay, that means what? If the input signal has a stronger amplitude, that means when the receiving antenna is close by your transmitting antenna, the loop gain goes up. That is not a very desirable thing. In case if the receiving antenna is very far away from the transmitting antenna, then the signal strength goes down. Okay, weaker amplitude, then the loop gain goes down. Okay, therefore what we have to do is we have to design a loop for operating to a certain signal amplitude, and if the signal amplitude changes, the value of kT changes, then all your system is gone. Therefore you have to make the loop gain independent of the signal strength. So dependence of design of input amplitude is not desirable. Okay, now how can we remove this independence? Because AC is varying. Varying means what? AC is the function of time. Okay, sometimes it is larger and sometimes it is lesser. So therefore, in order to remove this time dependence, we used one device that is called a band limiter, band pass limiter. Okay, therefore to ensure that the input signal always has a constant amplitude, we did something, right? That is, the input FM signal always has a constant amplitude. So what can we do? We can do employing a band pass limiter. So we can precede the phase locked loop by a band pass limiter, that is hard limiter followed by the band pass filter. Okay, therefore phase locked loop must be preceded by a band pass limiter. Band pass filter. Okay, and one more point I would like to point out here. In the voltage controlled oscillator, the output is, we said, A times V times sine of omega ct plus theta of t, and in the phase detector, the input is, we said, AC times cos of omega ct plus phi of t, if you recall this. In one place I have taken the cos function, and in other place I have taken the sine function. Why? Okay, so I have taken the input signal to be a cosine function, and the output of the voltage controlled oscillator to be a sine function. Why did I do that? So it depends on how you realize your phase detector, and in our case we realized our phase detector by using a multiplier followed by low pass filter. Please recall this, low pass filter in the output. So if I use both of them, cos and cos, then again I will get in terms of cos function, right? If the input carrier is cos 2 pi fct, the VCO output will also be, the VCO output will be sin 2 pi fct, then this will automatically happen because you have a closed loop, and the closed loop will work like that. So when I multiply cosine with the sine, I will get a difference components which will be sine, right? So cos of omega ct plus phi of t multiplied by sine of omega ct plus theta of t, then this will be equal to what? Cos A sin B. Cos A sin B is equal to sine of A plus B 2 omega ct plus something sine of a minus b, right. So if on the other hand, if I multiply cos of omega ct plus phi of t multiplied by cos of omega ct plus theta of t, then what will I get? I will get cos a plus b plus cos a minus b. Cos a minus b. Therefore, the cosine function, we know cos of minus theta is equal to cos theta, right. So the cosine function will not be sensitive to the sign of the argument, right. There is a sign, that sign of the argument will not be captured by your cosine function. Okay, so when I multiply cos function by another cos function, I will get cos of this argument plus this argument, and cos of this argument minus this argument, first argument minus second argument. So in that case, when I get some negative value, that negative value will not be captured by your cos function. So that is the reason one guy is sine and another guy is cosine. Okay, therefore your cos function will only decide the magnitude of the phase error, and you cannot track the phase. So in order to track the phase, we are using the sine function at the output of your voltage controlled oscillator. Therefore the phase locked loop will not be able to work properly if I choose here also cos and here also cos. If both of them will be cos, then the phase locked loop will not be able to work properly, because it must not only know what is the phase error, I need to know the sign of the phase error. Okay, so the phase error can be driven to 0. It must also know whether the phase error is positive or negative. So you want to be sensitive to the phase error, so it is also automatically works like that. So in a locked condition, it is implied that if the signal is cosine, the output signal will be sine, then there will be pi by 2 phase shift between the input signal and the demodulated signal. So that is the reason we used one is sine and another one is cos. So the input carrier is cos of 2 pi fct, and the output of your voltage controlled oscillator is sine of 2 pi fct. So this will automatically happen because you have closed loop, and the closed loop will work like that. A few more points, maybe 3-4 minutes. Now the next one is, now what can we do about the removal of this disadvantage of the first order loop, right. Till now we consider PLL without a loop filter. So we got a first order loop. Okay, another consequence of that is that loop transfer function. What is that loop transfer function? We got kt by s plus kt. This is what we got, right. What is this? This is the first order TF means transfer function. So that is why we call it a first order loop, because the transfer function is first order transfer function. So this loop is called first order loop. Okay, it has disadvantages that we have already seen. So there are two basic disadvantages which lead to non-optimum performance. One is a limited lock range, and the second is non-zero steady state phase error. Limited lock range, and the second one is non-zero steady state phase error. Okay, so these are the two disadvantages. Limited lock range and non-zero steady state phase error. So these are the two disadvantages that we already discussed. Now can we do something about it? How can I overcome this from these disadvantages? As I mentioned, we can try to remove both of these disadvantages by using a loop filter. You put a loop filter, one more loop filter of appropriate kind. To illustrate that, let us consider a loop in which we choose a loop filter with a transfer function like I am introducing one more loop filter with a transfer function s plus a divided by s. Okay. So this is the transfer function not of the loop, one of the filter in the loop that we are going to insert now, which we were omitted in the discussion. Okay, so this I can write as s by s plus a by s, then s by s is 1 plus a by s. I can write like this. And now from this you can see essentially 1 by a by s is an integrator, right? So a by s is an integrator. The first part 1 is a direct connection which allows the input signal to just go to the output. So such an integrator is called a leaky integrator. So you have input, the input is given to the integrator, you will get output, and you have one more output also like this direct connection. So this is called a leaky integrator because it allows the input signal to leak through the output as well as the component that will come after the integration. So this essentially what is called a leaky integrator. So f of s is equal to s plus a divided by s is called a leaky integrator that we are going to insert in our block diagram. So basically your linear model, let's consider the linear model for the simplicity of the discussion because the non-linear model will become very complex now. So the differential equation will be second order differential equation now because of this extra factor, because one order differential equation is contributed by this leaky integrator. Okay, and one order differential equation is contributed by the relationship between the VCO output and the VCO input. VCO and this one and this one. So from this I will get a first order, and from this I will get a first order. If you combine these two guys, I will get a second order. I will get a second order differential equation. Okay, and the phase plane plot will be much more complex now. When the equation becomes second order plot, then it is little difficult to analyze. Anyway, we will not go into that situation. So we will consider the steady state operation. I will at least prove through the steady state argument. Okay, using your initial value theorem and the final value theorem. Okay, therefore your block diagram will become like this: phi of s, Laplace transform of phi of t, then summation, this is plus and this is minus, and this one is theta of s. Here you have 1 by s, and this one is k suffix t, and here we put a straight line. Instead of that I will put a leaky integrator. Okay. Okay, previously this block was not there. Now we are inserting this block. Okay, f of s, and then it comes like this. So this is called a linear model. We are using the linear model and inserting this guy. In the linear model we are inserting this block, extra block. This one is extra block. Because of this extra block, your first order equation transfer function, where is your first order h of s? It is over here. So this is my first order. This becomes now it is going to be second order now because of the insertion of your leaky integrator. That leaky integrator is here. This is my leaky integrator. So what is a linear model for this? I have removed the sinusoidal non-linearity here. See, there is a sinusoidal non-linearity here that I removed. Sinusoidal non-linearity is removed. Okay, so there was a non-sinusoidal linearity, sign of the error function. Okay, so I am considering a linear model. So the input is phi of s and the VCO output is theta of s. Okay, and KT, what is KT? KT is a loop gain. So I am denoting it by a block. So what we are now introduced additionally is this guy, this loop filter with the transfer function f of s. Now the output of this loop filter is fed to the input of your voltage controlled oscillator. The voltage controlled oscillator is denoted by 1 over s. Okay, so the voltage controlled oscillator will be represented by a transfer function of 1 over s. Okay, I am taking the demodulated output from this point. Let me use a different color. So this is my demodulated output. I am taking the demodulated output and feeding into the voltage controlled oscillator. Now let us try to find out the closed loop transfer function for this case after introducing the loop filter. Okay, therefore h of s equal to phi of s divided by theta of s divided by phi of s. To find this, let us proceed step by step. Okay, let us write down the expression for theta of s. What is theta of s? Theta of s is equal to kt times f of s divided by s multiplied by the difference phi of s minus theta of s. So let's rearrange this guy, this equation. Then finally you will end up with the h of s after rearranging. Okay, do the manipulation, algebraic manipulation. You will get a kt times fs divided by s plus k suffix t times f of s. Now substitute for f of s, then it will become kt times s plus a divided by s squared plus k suffix t times s plus kt times a. This is my h of s. Now what is this? This is the second order transfer function. Okay, so it becomes a second order loop. So previously it was first order loop, now it becomes second order loop. So when you use a first order loop as a loop filter, the loop becomes a second order loop. So the loop transfer function has a denominator degree, which is how much? 2. So we are interested in to look at the phase error. So it will be interesting to look at psi of s, the phase error. So the phase error, what is the phase error? Psi of t is equal to what? Phi of s minus, let me write down the transform domain. I'm sorry. In the time domain, your phase error psi of t is equal to phi, I'm sorry, again I'm writing nonsense. Delete properly. Phi of t minus theta of t. Take Laplace transform. If you take Laplace transform, psi of s is equal to phi of s minus theta of s. Now I want to consider the transfer function, let us say between psi of s and the input phi of s. That will become 1 minus h of s. Okay, I would like to find out psi of s divided by phi of s. This will be equal to what? If you rearrange this, then it will become 1 minus h of s. Therefore, psi of s divided by phi of s is equal to, if you substitute 1 minus, what is your h of s? H of s is kt times s plus a divided by this whole thing. You substitute here 1 minus h of s. So the final relation, let me write down. These all are algebraic manipulations. So it will be the numerator a squared, the denominator a squared plus k suffix t times s plus k suffix t times a. So let me say this is equation number, I don't know, I forgot the equation number. Let's say equation D. So from equation D, can I say something about the steady state phase error? This is in the transform domain, okay? Psi of s divided by phi of s. You take phi of s to the right hand side. What is my steady state error? This is my steady state error. Therefore, psi of s equal to s square times phi of s whole divided by s square plus k suffix t s plus k suffix t times a. Now, how can I find out the steady state error? Steady state error means psi of t when limit t goes to infinity. That's what we mean by steady state error. At final, what is my error? So there is a, either you have to take inverse Laplace transform, and allow t to go to infinity, or you can use final value theorem. Final value theorem of your Laplace transform. So what that final value theorem of Laplace transform says is, your steady state error psi ss is equal to limit t goes to infinity, psi of t is equal to limit s goes to 0, s times psi of s. Okay, so to do that I must consider some kind of input. So what is my input here? This is my phi of s. You consider some kind of input and substitute there, then you can find out the steady state error. Okay, let us consider some kind of input that we are talking about earlier. Let us say the input frequency is a frequency step. Okay, so if the input is a frequency step, what can you say about phi of t? The input frequency is a frequency step. What happens to the phase? The phase will be integral of that frequency step, right? The phase will be integral of d phi by dt, and d phi by dt has a frequency step. D phi by dt has frequency step. Now what is my phi? Phi is the integral of my frequency step, right? Okay, so frequency step itself means that the Laplace transform of, let's say, u of t, if you recall the Fourier Laplace transform, this is 1 by s. Now the integral of u of t, it becomes, you will get another 1 by s, so it becomes 1 by s squared. Okay, so you are applying delta omega times u of t, so delta omega times u of t becomes, let me write down clearly. So we are applying input m of t is equal to delta omega times u of t. Okay, so what is the relation between m of t and phi of t? D phi of t by dt is equal to m of t. Recall this relation, because your phi of t is equal to 2 pi kf integral of m of tau d tau. D phi of t by dt is equal to 2 pi kf times m of t. Now forget about this constant. Now my m of t is delta omega times u of t. Therefore, what is the Laplace transform? Let us say m of f, capital M of f, s, is equal to delta omega divided by s. Now m of t is equal to d times phi of t by dt. Now take Laplace transform on both sides, then this becomes m of s. This is equal to 1 by s times phi of s. Okay, so no, let us not confuse too much. So you are differentiating. So if you differentiate, then what will happen? You are multiplying one more s, therefore your phi of s is equal to delta omega over s squared, because you are integrating the m of t. Okay, I mean it's very simple, right? Okay, so don't worry, confused with that. So what I am saying is your phi of t is equal to integral of, let us forget about the constant for the time being, m of tau d tau. Now if you take Laplace transform, then your phi of s becomes m of s divided by s, right? Because integral of m of s. What is your m of s? M of s is the delta omega times 1 over s. So 1 over s times delta omega over s, therefore delta omega over s square. This is my phi of s. That's it. So substitute this value in this expression. Where is it? In this guy. Okay, so therefore s squared times delta omega divided by s squared whole divided by s squared plus kts plus kt times a. So s squared will get cancelled. You will get delta omega divided by s squared plus k suffix t times s plus k suffix t times a. What is this? This is my phi of s. Sorry, psi of s. Input, right? Psi of s. Now use the final value theorem. So what is your final value theorem says? Psi suffix ss is equal to limit t goes to infinity psi ss of t, and this is limit s goes to 0 s times psi of s. So therefore limit s goes to 0 s times the whole thing, delta omega whole divided by s square plus k suffix t s plus k suffix t times a. So when s goes to 0, then this becomes your steady state error, psi ss equals 0. So this is what you want now. Similarly, you can argue, okay, I will leave that as an exercise for you to complete that. The steady state frequency error would be 0. So in this case, same argument, like this is steady state phase error. You can similarly argue that steady state frequency error is equal to 0. We can prove that. It's a simple proof. Okay, in fact that is trivially obvious from this, because frequency error is going to be the derivative of the phase error. Now if you take the derivative of the phase error, already the phase error is 0. If you take derivative, then obviously it would be 0 steady state frequency error. So the second order loop removes both the disadvantage of the first order loop. In the first order loop we had a problem. What is that problem? We had finite steady state error. If you look at, go back, we said two drawbacks, if you recall, limited lock range and non-zero steady state phase error. These two drawbacks can be removed by the second order loop. However, the only difficulty is the complexity of analysis. So this analysis that we have done is a very approximate linear analysis, and this linear analysis is valid around the locking situation. That means when the loop is really in the lock. so that the linear approximation can be assumed to be valid. Otherwise, the proper non-linear analysis is needed. Of course, the non-linear analysis will be somewhat difficult. And finally, you will reach the same conclusion what we got now. Okay, so I think more or less we have completed this phase plane plot. So I think that is the sufficient discussion for the phase locked loop. So elaborately we discussed on phase locked loop. And one more important point, that this is not the only kind of feedback demodulator. Okay, so phase locked loop is not the only kind of demodulator. We have yet another interesting feedback demodulators, that is called frequency compressed feedback demodulator. So this is another very interesting variant of PLL. In fact, that is the variant of PLL, but which is often used for demodulating FM signals, more or less for the same purpose that the PLL is used. Okay, which is called system with frequency compressive feedback, and this one is similar to our phase locked loop, but there are some major differences. So in the next lecture we will talk about yet another type of frequency demodulator, which is called frequency compressive feedback demodulator. That's it. Okay, so let me stop at this point. Thank you very much.